Hello everybody. I just want to run through this section 7.1 notes about the normal distribution. And this is going to be a little bit different than what you were doing last with the binomial distribution, because here we're going to be talking about continuous variables for this one, but we're still, of course, interested in calculating probabilities using this one. So there are a couple of things about it. These two rules right here that you see, they sort of are the same as just probability rules in general. For example, the height of the graph needs to be more than 0, because here the height of the graph is having to do with probabilities. So probabilities are always more than 0 anyways. But really for this one, to calculate probabilities, we're more interested in areas than the actual height of the graph. We're looking for the area, because you'll notice this other rule, which is the important one, is that the area under the normal distribution is going to be equal to 1. And that's because the area under the whole graph, you see the graph down here, the area under there is supposed to be the probability of basically the sample space, which should be 1. And so if you look between two particular values of your variable that you're talking about, if you find the area that's between two values, that will be the probability to get a value that's between those two. And the important thing about that is that here we're talking about a continuous random variable. So remember, with the binomial distribution, we were not talking about continuous variables. We were talking about, can you remember the other kind? It should be discrete variables, which are the ones that give you usually a whole number of values. So, examples were these trials about, having a child or something, whether it's going to, how many of the children are going to be girls. So normally in a family, you can have like 0 girls or 1 girl or 2 or 3 or 4. But here for a continuous variable, these are the ones where you can get decimals and you can get all kinds of values in between stuff. So this would be, if you're measuring with a scale, like measuring rocks, how much they weigh or something, then you can get all kinds of milligrams and 0.001 and all this. So here we want to know the probability to get a range of values, because if you think about it, say for example, we go with that example, we're going with measuring, how much rocks weigh, like grams and milligrams. If you just go outside and you pick up a rock and you wonder what's the probability it's going to weigh 20 grams. Well, really the probability is pretty much 0, because you can get all kinds of weights. You can get like millions, and really, depending on how accurate your scale is, you can get infinitely many particular weights. So the probability to get one specific weight is 0. And if you think about it, that's because, say for example, on this graph down here, the 20 gram rock, maybe it's this value, and the area of just the line that goes directly above this one, it's just a straight line. And straight lines, they really don't have an area. You need to have a little range where maybe we say, well, what's the probability to get between like 19 and 20? Well, now that it's these two lines, you kind of have, a bit of an area between these two, where now you can figure out what's the area of this little spot between these two values, and it will have an actual area. So enough about that one. We're talking about now the properties of the normal density curve, and that's what you see down here. It's the bell-shaped one. It's of course symmetric about the mean, so the mean will always be right in the middle. It's symmetric on, both sides. The mean, median, and mode, they all are in the middle because of this kind of symmetry that we have. And then we don't really, inflection points are kind of here and here. That just means when it goes from being kind of concave down like this one to on the tails being concave up. And then the area under the curve is 1. We also have that to the left of the mean, that's half the area, and then to the right of the mean, that's the other half. We also have that these tails, they should be getting lower and lower, almost to 0. The height of them should be getting close to 0, but for the normal curve, if you saw the actual function that it is, it has an asymptote at 0, so it's kind of asymptotically approaching 0. It will never reach there. It will only just get super, super close to 0. And then we also are able to use the empirical rule for this one. We pretty much won't have to remember the empirical rule that much because we're going to always be using the calculator. But we will see some examples for this one.